This video is how to perform tolerance allocation and percent contribution in the Monte Carlo simulation feature in Quantum Excel. It is part of a series of videos on Monte Carlo simulation, and a link to that series is in the description below. For this example, we're continuing the example of the resistors in parallel. We have modeled R1 and R2 with a certain mean and standard deviation, and we've already performed the Monte Carlo simulation. There are videos in the series page that show how to do both of those, but you need to have already run the first Monte Carlo simulation before you're ready for the percent contribution or the tolerance allocation. When we ran the Monte Carlo simulation, what we found was that the standard deviation of impedance was 1.13. And an interesting question is of the variation in each of my resistors, so for example, I have currently modeled R1 as normally distributed with a mean of 300 and a standard deviation of 2, and I've modeled R2 with a normally distributed with a mean of 100 and a standard deviation of 2 as well. Because the only factors in my model are R1 and R2, the variation in R1 and R2 is definitively causing this standard deviation of impedance of 1.13. But the question is, how much of that is coming from R1 and how much is coming from R2? For example, if we wanted to buy a better resistor to reduce that variation, would our money be best spent on buying a lower percentage resistor for R1 or R2? To do that, I can do it two different ways. The simplest method is to come up here to percent contribution tools and choose percent contribution and choose the number of simulations. In this case, I'll just go ahead and run 1 million simulations. And when I'm done, Quantum Excel will calculate the percent contribution for me. In the upper left-hand corner, it tells you that the name of the IPO sheet was sheet 1, and that the engine was the Quantum Excel Banyan Tree engine in rocket mode. See the video on how to interpret the results of a Monte Carlo simulation for what those factors mean. Additionally, it's still using the Mersenne twister random number generator, and it did 1 million simulations in 6.61 seconds. Down in the lower right-hand corner, we can see the results. The results are the percent contribution. So the variation in impedance, how much of that variation is coming from each of the variables. In order to see that better, I'm just going to hide these rows, and that makes the plot easier to see. In this case, we can see that R2 is responsible for almost all of the variation. If I hover the mouse over the top of it, we can see that the actual number, the value is 0.988, which means that R2 is responsible for 98.8% of the variation, meaning that the last little bit of variation is coming from R1. In this particular case, if we wanted to reduce the variation in impedance, then we should tighten the tolerances, or we should work to make the variation in R2 smaller, because R2 is responsible for almost all of the variation in impedance. It is important to note that this percent contribution is about the variance or the standard deviation in impedance, not the mean of impedance. Another way to perform the exact same function is to go back to the model sheet and then click on QXL Monte Carlo percent contribution tools, and then click on tolerance allocation and choose the number of simulations. In this case, again, I'm going to choose 1 million simulations. Quantum Excel will then ask me what kind of defects per million it should use for the output impedance. The default is the normal DPM data, which is calculated by integrating the area under the normal curve. The alternative is a count out of spec data, which does not make the assumption of normality. See the video on how to interpret the results of Monte Carlo simulation for the difference between those two. In this case, I'm going to leave it as the default, which is the assumption of normally distributed. It makes the assumption the data is normally distributed, so therefore it uses the equation for defects per million by integrating the area under the normal curve. When I click on OK, Quantum Excel will then run a series of Monte Carlo simulations where it changes the standard deviation of the inputs, and then it gives us a summary of the results in the outputs when it is completed. When Quantum Excel is done, it will create a new tab called Tolerance Allocation. First thing you should note is that it gives you the same results for the percent contribution as we saw just a second ago. We can see here that R2 is responsible for about 98% of the variation, and R1 is responsible for the very small amount, less than 1%. As I scroll to the right, I get what is called a tolerance allocation table. Now, the tolerance allocation table The way I read this is, Quantum Excel ran the Monte Carlo simulation with the nominal values, and the nominal values were that the standard deviation, so R1's standard deviation is equal to 2, and R2's standard deviation is equal to 2 as well. When I did that, I got a 10 defects per million and also 10 defects per million when I ran a million simulations. Then Quantum Excel will take R1's standard deviation and reduces it by 10%, 25, and 50%. So by the time it gets to 50% reduction in standard deviation, that means that R1 standard deviation is now equal to 1. And when it did that, results of a million Monte Carlo simulations were 9. So we can see that reducing R1 standard deviation from 2 to 1 made almost no difference whatsoever in the defects per million. Additionally, it increases the standard deviation by 10, 25, and 50%. So when it gets to plus 50%, this means now that R1 standard deviation is equal to 3. And again, the number of defects per million hardly changed at all. It went from 10 to about 11, or call it 12. It then returns R1 standard deviation back to its default value of 2, and it does exactly the same thing now with R2. So it starts with a nominal, which is 10, and then it reduces R2's standard deviation by negative 10, negative 25, and negative 50%, and now the defects per million are practically 0. This would now be for an R2 standard deviation is equal to 1. And then it increases it by 10, 25, and 50%, and you can see that at plus 50%, the standard deviation of R2 being at 3 now causes 3,127 defects per million. You can see that changing the standard deviation in R1 has almost no influence on defects per million, but changing the standard deviation in R2 causes orders of magnitude change in defects per million. This table is now expressed as a graph in the plot to the left of it. So the vertical axis is defects per million, this is the nominal value, and this is the change in sigma for each of the inputs. The blue line is R1 and the orange line is R2. And we can see that changing the standard deviation has a much bigger change in the defects per million for R2 than R1. We would therefore say that the impedance is very robust to R1, but is very sensitive to R2. And this tolerance allocation graph is a similar story, but presented in a different way than the percent contribution plot that is on the left. And that is how you perform percent contribution plot and tolerance allocation in Quantum Excel.